Well, these are the solutions to the questions on page 226. And I'm just going to walk through them here, see if I can make them make a little bit more sense. So here, David spins a sling in a horizontal circle above his head. What would happen to the period of rotation? So that's the t, the period of rotation, if he applied the same force. And the length of the sling was doubled. So that means that the r is going to go to 2r. And here, halved. Here the r is going to go to 1/2 r. Now this is not easy, but and I mean, you wouldn't be asked to do this on a test, but I'll show you how it works. This is the kind of stuff, I mean, it's really kind of like a university level question. This is your equation for the centripetal force, F equals mv squared over r. When we rearrange that, we get the speed is the square root, and you can try this yourself, the square root of F times R divided by M. The period then is 2 pi R divided by V. Now we already have an expression for V here, and so we can bring that over here, and so the period is going to be 2 pi R over the square root of FR over M. So now we've got a general equation for the period. Okay, now, and again, like, you wouldn't be expected to memorize this. If you double the R, what I'm going to do here now is replace the R with 2R in the on top and also on bottom, and then extract it. So here the 2, this 2 can come out, and down here a root 2 can come out. And then what we have left inside, this is your original period right here. Okay, so that's the original period, and we've taken out 2 over root 2. So if you divide 2 by root 2, you get 1.41 times the original period. Okay, so you have, that's how it's going to change if you double the radius. And then if we go down here, if we halve the radius, in the equation that we had for period, I'm going to replace the r with r over 2, and down here again r with r over 2. Here the half can be dragged outside, right? You can factor it out. And down here, the half, which I put in here, will come out and become a 1 over root 2. And again, this piece, just have to ignore that. Here, this is your original period. And so we have a half over 1 over root 2, and when we rearrange that, we get root 2 over 2, and that's 0.707. So that's how the period changes if we half the radius, but we keep the force the same, right? That's the main thing to remember here. You've got to keep the same force. The only thing here that's allowed to vary is the radius, not the force and not the mass. Well, let's move on to number 16. The drum in a clothes dryer is a diameter of 0.7. First thing you want to do is, that here, that means that the radius is 0.35. And the period of rotation is 0.42 seconds. And so we have to calculate the centripetal acceleration. The centripetal acceleration, by the way, is the A is equal to V squared over R. And then so let's go down here. Your V is 2 pi R over the period. So you're given the radius, you're given the period, you can find the speed. And then once you have the speed, you can just plug that into your centripetal acceleration equation. The AC is equal to V squared over R, and we get 78.5 meters per second squared. And then another question is, how come the clothes don't fly in a straight line tangent to, how come they don't, so how's that phrased again? Why do the clothes not fly toward the center of the clothes dryer? And it's the normal force is always pushing inwards, but the clothes, what they want to do is fly in a straight line tangent to the radius, according to Newton's first law, right? The law of inertia. And the only thing that keeps them from doing that is the normal force that keeps pushing the clothes towards the center. In the next one, in number 17, we're asked, we're given the distance of the Earth from the Sun, and we know how what the period of the Earth's orbit around the Sun is. It's 365 days. So doing that, we have our radius, we have our period, which we convert into seconds, and then we can calculate the centripetal acceleration by plugging in the v that we found. Oh yeah, I found the v up here. So there we go. I found the v first, and then I came down that way. So the v is 2 pi r over t, right? And we had the period here in seconds. Kind of did this out of order. First I went here, and then I came back this way. So this is kind of like step 1. There's step 2. There's step 3. And then we eventually end up with the acceleration. And the acceleration is very tiny. So look, we calculated the v of the Earth going around the Sun. It's actually 108,000 kilometers an hour. That's how fast the Earth is moving through space. And the acceleration here is very tiny, right? It works out to be 5.96 times 10 to the negative 3, which doesn't sound like much, but it's occurring every second, and it adds up over hours and days. So it's enough to keep the Earth in a curved path around the Sun. Number 18, the maximum speed at which a 1,500 kilogram car can round a curve on a flat road. The radius is 90, and the coefficient of static friction is 0.5. Well, and then it asks if you need the mass here. Well, I mean, we can calculate the force of static friction at that, right? Like we had the mu and we had the Fn, and there's the force of friction on that car. That's the force of static friction, mu Fn. And so you would need to exceed that force in order to get that car to skid. But if we do it this way, our free body diagram is just going to have one force, the force of friction going that way. And just like we did on the assignment, the mv squared over r is going to equal to mu s times mg. The m's cancel out, and we end up with an equation here for the speed at which these two things are equal to each other. And it's 21 meters per second. And you don't need the mass at all. So 21 meters per second is the speed where the force of static friction will equal this value, 7360. And if we go faster than that, we're going to exceed the force of static friction, and the car will skid off the road. In number 20, you get a vertical loop, radius of 10 meters, and you're being asked to calculate the at what speed people will start to drop out. So this is at the top. The net force is the mg plus the Fn. The speed at which people will drop out is where the normal force drops to 0. And then the equation reduces down to v is the square root of rg, and we get our speed pretty quickly. In number 21, we're asked to find two things. What is the maximum tension at the bottom of the swing, so down here? One, when it's just hanging. You just allow that mass to hang. And when you do that, the tension is just equal to the weight, right? Because there's nothing else happening. It's just, it's just hanging straight down. But when we're moving at 2.4 meters per second, when it's actually like in motion, in a circular motion, the tension has to be greater than the weight. And so here the F net is going to equal force of tension minus mg. And then when we rearrange, we get 9.71. So it's increased quite a bit. In number 22, we got a rope attached, and we got to find the maximum and minimum tensions. This is exactly like what you did on the assignment. Your normal force, your F net at the bottom, your F net at the top. Rearrange everything. So this one here is pretty familiar to everybody. In number 23, we got a pilot experiencing 9 Gs. So that means that the acceleration is 9 g's. 9 times 9.81. And the centripetal force would be 5,300 newtons with 9 g's. So here now we have our F net is mv squared over r and 95.2 meters. And then 24 we haven't done yet.